intelligence. We're going to talk a lot about that, but then we're going to add that to graphs, which graph technology has been growing quite a bit in the last, definitely a year, in the last few years especially as well. And so we're going to look at combining these two types of technologies and seeing the power and the value you can get from using these two together. My name is Jennifer Reif. I'm an engineer for Neo4j. I really enjoy writing the tools and the extension libraries that go along with our Neo4j database and other products. My team writes a lot of the open source tools and extensions. So I enjoy writing code for those types of things, and then I enjoy writing about it, the things that I've learned and the code that I enjoy writing, and then coming out and speaking about it to places like this. Absolutely beautiful. I recently got introduced to this topic probably about a little over a year ago, when I co-presented with a colleague of mine who's really into the mathematical and theory side of things. I don't have really a strong background in math, but just the logic and the understanding that goes along with this topic area in general is really fascinating and really powerful. So I really love to talk about this topic. And of course, just as a side note, personal about me, I enjoy cats, coffee, and traveling. And so I'm thrilled to come out here and speak to you guys and drink a lot of coffee. And I'm sure my cats are missing me at home, but they'll get extra cuddles when I get back. So we do have a limited time today to talk about this, but please do feel free to reach out to me either via email or Twitter or LinkedIn, however you're most comfortable. I'm happy to continue the discussion and answer questions or talk about other topics or various interests in the technology space. So we're going to start with just kind of a high level of these three main topics, and we're actually going to cover all three of these today, but we're going to start just kind of looking at an overall definition. So the way I and some of my colleagues at Neo4j like to think of it is that artificial intelligence is a little bit of a broader category. It's just looking at how computers solve very specific tasks in different ways to mimic and make it similar to human decision making. Typically, because computers don't handle context and a broader kind of solution and data points very, very well, typically artificial intelligence right now is used only for specific tasks and examples. So again, computers don't really calculate all that broader context and things like we humans do, at least as of yet. So right now, they're used specifically to handle certain tasks, and they do that very, very well. Machine learning, which is kind of a little bit more specific than that topic, is really about iterations and letting computers learn based on the iterations and the results that they get from each iteration. So it's about repetitive processes, having machines execute a task, looking at the results, saying, can I improve this? Is this better than what I did before? And saying, okay, because of these results, now I can process this way. So because of this, it takes on a lot of data. And it just constantly looks at improvements. Deep learning, even more narrow and focused than that, is looking at processing layers. So it's stacking up and trying to condense very complex max amount of data into something that a machine can read and understand and use for learning. So it's basically trying to take these complex ideas or these complex data sets and condense them and flatten them down to something that then can be used for comparisons or for other types of processing. So again, we'll get into a little bit more of this, but this is just high level of what we kind of see as these terms, all these buzzwords kind of meaning. So first off, before we dive too far into this, is some of you may not be aware of what a graph is. Graphs are not what are shown on the right-hand side. They're what's shown on the left-hand side. So a lot of times when you tell somebody Neo4j or other types of graph databases, they're like, oh, cool, it stores pretty pictures or it stores dashboards. No, what it's actually doing is storing data as entities and the relationships between them. So it's elevating and bringing those relationships to equal value as the entities themselves. Where on the right-hand side is what we call a chart. So I even catch myself occasionally wanting to call those graphs, and I can't. That's a huge no-no. I always think of that now. It's the first thing. But where did this stuff come from? So it was built on the research and mathematics of someone called Leonhard Euler, who lived back in the 1700s. He was a Swiss mathematician, and he came up with, I don't know, you guys may have heard of the 7 bridges of Königsberg problem. So basically, there were 7 bridges connecting these 4 land masses, and he wanted to determine, can I cross each of these bridges one time and return to the starting point? So he mapped it all out, he modeled it. What do most of us do? We go to the whiteboard. It's kind of what he did, and drew it all out and realized that really the important pieces of this problem are the entities, the land masses, and the bridges that connect them, the relationships. And so this actually sparked what's now considered graph theory, the mathematical study, network science, and graph theory. The idea that we have nodes and entities that are then connected to relationships, and the relationships or the bridges are actually equally important to the entities themselves. So just a few examples of how this is used in real life. This is an infrastructure graph for AWS. So you have various regions that have different pricing for certain services. You'll have different services that are available in that. You'll have availability zones. You'll have continents that those are available in. And so you can kind of see kind of this flow down structure of how AWS is connected and how it works. A little bit more serious is a bank fraud graph. I know it's a little bit hard to see the text on this one. But we have account holders here in the larger circles, these 3. And you can see that these 3 account holders share an address. You even have 2 account holders that share a social security number. That's definitely not a good thing. And some other things that look a little bit suspicious. And so using this type of network structure, you can find fraud rings, you can find fraudulent activity and transactions that are occurring because you can see the relationships here. So going to a little bit of a lighter note, if I wanted to create a travel graph, so maybe I wanted to take a trip, or maybe I wanted to kind of keep track of the trips that I had taken. And so you might want to take a trip to a particular country or place or city. You might look for places to sleep in those areas. You'd look for food and how much that food is going to cost you. You'd plan the trip itself, how you're going to get there and how you're going to get back, how much that might cost you, and you'll kind of plan this entity of trip. So hopefully you can kind of start to see how this might be used for analysis. But let's go back and just talk about data analytics in general for a second. So the reason that data analytics is so complicated is that data structure is extremely hard to unfold. It's extremely hard to unpack all of that information and find the important and the valuable bits to make some decisions. Even if your data isn't structured in tables or documents or data lakes, even if it's structured in a graph, you can see that this connected ball of spaghetti up here, that's really hard to untangle. It doesn't make a whole lot of sense to us. We don't know what to focus on because it's just kind of jumbled. So there's a few different ways that we approach data analytics right now, currently. So you can put it in something like relational databases, traditional database type of structure. It does really, really well for scaling lots of rows, up to millions of rows, and then doing some joins across those. But it starts kind of falling over a little bit as you start adding millions and millions and millions of rows across tables, and you start doing about more than 3 hops across joins. It just starts to kind of get a little bit, kind of fight one another. So you kind of start to see the performance of SQL queries kind of just ease down a little bit. So another option to kind of handle this a little bit better is our big data technology. So things like Spark, things like other types of data lakes and tools to kind of crunch all of these numbers, handle a lot of the filtering and the aggregation that maybe our relational databases couldn't handle very well. But the problem is it's crunching so much data, you end up with these really long-running queries, and you continue to filter and aggregate a lot of very complex decisions and maneuvers, and it starts to have trouble at some point too. The problem with this is that a lot of the calculations that are made out of these types of data structures are using averages. They're calculating up, okay, what are all of these values? Can I just find just an average, and let's go with that. So if it's greater than 50%, we're going to say, yes, we're going to do this. If it's less than 50%, no, we're not going to do this. And that works reasonably well. But the problem is that averages really aren't reality. So you see in this chart that we have a natural bell curve. Nice, pretty, even bell curve. But this is an average distribution, or what's called a random distribution. The problem with this type of distribution is that there's not a single network in nature that actually fits that structure. So why are we analyzing data in a structure that makes no natural real-world sense? What we actually see in the real world is a power law distribution, something like a scale-free network or even a small world network, where you have a lot of entities and you have a few entities that have a ton of connections, a bunch of entities that have very few connections, and then some kind of here in the middle. So nice, pretty bell curve. Or nice power law distribution, excuse me. Bell curve's on the left. So for those of you who aren't overly familiar with the mathematical, like pictures better, I do too, don't worry. Our average distribution is here on the left-hand side, drawn as a graph, or a diagram if you like. And so that doesn't even naturally fit our eyes. Our eyes and our brains don't really like that picture because it makes no sense to us. Where on the right-hand side, that scale-free network and the small world network, those make much more sense to our eyes and our brains because our brains handle patterns very, very well. So they naturally make sense. They naturally are appealing to us. So these are the types of structures that we actually see more so in the real world. Scale-free network is no matter what size of the data you're looking at, the structure and the connections look similar. They're reasonably the same. And then small world network, as you can see, is that very hub and spoke, interconnected and very dependent, which you see in a lot of type of social structures. So you can see this a little bit better here, where you have that natural average bell curve here, but you're missing all of these entities here and all of these entities here. So graphs allow us to invest in those populous areas, those that you have a ton of entities there that have very few connections, so they don't fit that average block. And you have strategic entities that are very, very highly connected. You're going to miss those too in that average distribution. So things like the hub of a city, maybe you want to focus your event or your time and your efforts in something that's very, very well connected in the city, or a person to get information distributed through your network, someone who's very highly connected, has a lot of friends, they would be a great one to push that information through. So you're going to miss that in an average distribution. So we have our regular data analytics tools and processes. Those work well for a lot of cases. But we could add something on top of this. We could add the graph, which shows us those network structures, gives you those real-time connected insights up to millions and millions, which is really nice. The reason this handles data so well is typically when you're running some kind of query or algorithm or et cetera, you're only looking at a portion of the graph at a time. Right? Even when you query tables, you're really only looking for a subset at a time, but you still have to go through those millions and millions of rows of data. Where a graph, you only look at the relevant nodes. You're not going to touch everything else in the graph. You don't need to. So that's why it handles those types of network and pattern structures so much faster. So the idea here is that it's not really what you know about the data, it's what you're connected to. So for instance, if you were to take one common example right now is predicting whether someone's a smoker or not, or someone's going to vote or not. Actually, it's not where they live, where they work, what degree they have, et cetera. That's a good predictor of whether someone will smoke or whether they'll vote. It's actually who they're related to in their family and friend connections. So whether the people around them smoke or whether their friends vote, that is a better predictor of whether they're going to do that or not. So this is where we combine the two, and we're looking at graphs as well as analytics. So we're applying this network structure to this process of analysis and really crunching this data and bringing real value and insight to this. So graph analytics is just basically using graph-based approaches to process and look at this connected data. Does anyone know what these graphs have in common? They're the same. It's called isomorphic. So basically, as you can see, this one on the left-hand side, probably most of you appeal to the best. It makes the most sense. And again, it's that brain pattern matching that's so natural to us. Where on the right-hand side, that structure is harder to tell. It's not as easy to see. Simple isomorphisms, like the one up on the top there, is pretty easy for your brain to kind of untangle. It's kind of like a puzzle. So this one here, you can kind of see how it's this structure. You can kind of unfold those relationships and make sense of it. This one down on the bottom-hand side, not as much. It's a little bit harder to tell that one. So that's where something like graph algorithms really helps you unfold that structure and make more sense of these very complex and very densely populated problems. There's a couple of different approaches to graph analytics. You can run something like just a simple query in the graph, but typically that's something where you know what you're looking for. You know what might help you get your answer. You know what area of the graph to traverse. So typically this requires something like a subject matter expert or a data analyst, someone who's very familiar with the domain. As you start getting toward the right-hand side there, if you're just looking at overall structure, you're not as familiar, and you want to know what the structure is of your data because you're not familiar with that data set, that's where you need something like graph algorithms to tell you what that structure is and help you decompose those very complex kind of groups. So this is just one example, and it is kind of a stark contrast. I'll help guide through that in a second. So on the left-hand side here, well, actually, this entire thing is Game of Thrones data. So my colleague, Will Lyon, took the Game of Thrones data set from the books. I think it might have been, I don't know if it was books 1 through 4 or just book 1, but he dumped the character data into Neo4j, as you can see there on the left-hand side. So that's just all the characters and the interactions between different characters dumped into Neo4j. Now, as you can see, it's probably pretty hard to untangle that. You can kind of see over here, this is Daenerys' node. You can kind of see she has her own little grouping. She has her own little community of people around her. She's kind of separated from the rest of the world. And if you look, it's really hard to see. I think Tyrion might be there in the middle. That's kind of a spaghetti ball. So it would be really hard to kind of untangle his community and the connections and relationships connected with him by just looking at this. So what my colleague did is he ran graph algorithms over that data, calculated some of the results that came out of those algorithms, and then pushed that over into a visualization tool. That's why it looks so pretty. Otherwise, you could just get the results back, and it would show you numbers and calculations and stuff. But this better shows you how that data breaks down. So you can see the color is now your communities. So Daenerys' community over here in green, you can see exactly which characters are connected to her, and they're not connected to other communities. Here in the center, you can see Tyrion's kind of community here, and all the people associated with him, etc. The larger the node, the greater the page rank. So how much influence does that character have? How many connections do they have across the graph? And then finally, the thickness of the relationship is just the number of interactions. So it's basically a calculation of the weight property. But you can really see then how many times characters have interacted just by looking at the visualization. So again, this is a prettified version of what the graph algorithms are going to give you, but that still allows you to understand which nodes are most influential, how your data structure is composed, how it breaks down, and then where to focus in for your analysis. So graph algorithms allow you to do this. Basically, all they are implementations, technological implementations of network science algorithms. So stuff that mathematicians have been doing and students and academic professors have been studying and researching and writing papers on for years, we're actually applying them now to technology. So if you look at network science, it's all, quite a bit of it is dealing with graph theory. And this just allows you to enable reasoning over the structure. You can look at things like bottlenecks and influence and groupings and potential connections even, pathways, and tons more different things. Typically, you're unsupervised, so you'll run the algorithm. You might pass in certain kind of parameters as far as the boundaries of the graph you want to search, but then it knows what network structure to look for. So it will run over the algorithm. You don't supervise that. You don't tell it how to do it. And we've kind of segmented them into different categories. So we have community detection algorithms for looking at how a community is clustered together or breaks apart. We have centrality algorithms looking for importance or influence of particular nodes in a network. Link prediction for looking what are the relationships that I currently have in my data, and can I predict where there might be a new relationship? Similarity is literally just a calculation of how similar are these two nodes or small networks. And then finally, pathfinding and search just looks at routes, alternate routes, looking at best route based on cost or weight or distance or however you want to define that. Now, Neo4j is not the only one doing this kind of thing. There are tons of other vendors and tools and libraries out there that handle graph algorithms that are looking at this type of analysis. These are just some of them. I'm speaking from Neo4j's point of view because that's what I'm most familiar with. So please do feel free to check out tools, check out our stuff, whatever you're most comfortable with. If you're already using some of this stuff, of course, that's an easier and more natural on-ramp. So typically how they work, at least at Neo4j, although I think this is somewhat standard across the board, is first of all, you need to figure out what kind of algorithm you want to run. Are you looking for a path? Are you looking for influence and importance? Are you looking at groupings in your data set? Then you'll want to look at what's my domain. So based on kind of the shape of the data, you might choose some different algorithms for that. Whether it's densely populated or sparsely populated, how interconnected is my data? If it's not very connected, there might be some other algorithms you might want to run. And then is it small or large? So some of the algorithms are rather CPU and time intensive. Do you really want to run that kind of thing at first, or do you want to start someplace else and kind of break it down a little bit and segment it out? So as I just mentioned, you can actually run the algorithms of the entire graph, which can be pretty intensive depending on the algorithm and the size of the data. Or you can actually run like a cipher query or some sort of what we call cipher projection, where you basically tell it a certain section of the graph to iterate that algorithm over. So that kind of can help you section out. If you have a lot of data, you can kind of create a boundary for I only want to run this algorithm over this amount of data. And then you can either return the results on runtime, so when you execute the query, it'll do all the calculations and return the results, or you can write those results back to the graph and run those and return the ad hoc queries in order to get those results back at some later time. So this works really well if you have a really massive graph. That would be very intensive for it to do all that calculation and return all of those results to you. That would be quite a bit. So you can write that to the graph and then just return like the top 10 or the maximum 50 or however you want to define that. So there's a few examples I want to walk through here. On the left-hand side, here's an example of the human malaria parasite. So you can see the top one, how it's kind of broken apart, and then as it changes down in that lower one, you can see it's better segmented as far as the entity types go. The one here in the middle is a species hierarchy. So you can see how the different species kind of group together or might be hierarchy type of structure. And then that last one is also a hierarchy, but it's looking at, can I tell where the missing gaps or missing information or missing links are in my data based on the structure that I already know is there? So a couple of real-world examples from customers and users that we've come across. This was a centrality algorithm that they ran. A company was having a lot of problems getting information across the company. They were finding that some messages were getting through really well, and other things were not traversing through the company at all. And so they were trying to figure out why this was happening. And so when they ran centrality algorithms over their network, this center node right there that seems to have a lot of connections and a lot of control was actually a quality assurance maintenance person. And whatever information was getting to him was suddenly getting out to the rest of the company. But whatever he wasn't relaying to the rest of the group, then that wasn't getting pushed out to the rest of the group at all. So you could see how if they wanted to influence and get out certain messages, they might want to target him and make sure he gets the memo. But likewise, if they want to fix the initial problem itself, they might want to try to find other ways to connect the different groups without going through him. Because you never know, he could pick up and leave the company the next day and you would have no communications left. It would be the end of it. Next one here is an electrical grid. As you can probably tell, in Italy, they were having problems with cascading failures across their network. And so what's kind of most businesses' reaction to cascading failures? Contingencies, right? You want to put in backups. You want to make sure things fail over correctly. You want to add in these extra layers to make sure things don't fall over. What they actually found when they ran centrality algorithms over this network was that if they removed 4 nodes, they improved their resiliency and their reliability. All of a sudden, you didn't have these cascading failures. And that's because those 4 individual nodes were spreading and cascading like a disease throughout the rest of the network. So when they went down, it just caused the next ripple effect to the next entities and knocked down the next nodes. So by removing those problem entities, they were able to improve their reliability. Finally, the last one here is a telecommunications network, a Belgian telecommunications network. So on the left-hand side in the green are, I believe, Dutch speakers. And you can see they pretty much speak to Dutch speakers. On the right-hand side are French speakers. They pretty much speak to French speakers. They make phone calls back and forth, in their own language. But as you can tell, here in the center, this tiny little connection here that's kind of zoomed in and maximized here, there's a few that actually cross those boundaries. So there's a few Dutch that speak to French, French that speak to Dutch. So you can imagine, I believe they ran Louvain algorithm on this data structure to find this. So you can imagine if you were trying to strengthen the relationships between these two groups, you would focus in on trying to broaden and increase the number of entities in that middle section. Likewise, if you were trying to break that apart and not let those two groups talk to one another, you'd focus in on breaking apart that group and breaking down those relationships. So as you can see, graph data science, using these types of structures, gives us better decision making. So using this type of network structure, you can come out the other side and understand I need to make this decision and this is why. So you can use graph algorithms to explore, plan, and measure your data. You can do things with it like find significant patterns or look for optimal structures or patterns. You can even score outcomes and set a threshold for over 70%, we're going to say yes. Over under 70, we're not. But you can also do things like machine learning with this sort of thing. So you can use those measures as features to train a machine learning model. And actually, we found that improves the accuracy. So let's talk a little bit about using graphs with machine learning. There was an article last fall that Google posted. They worked with, I think, their DeepMind group and MIT and some other very brilliant people. And so they were looking at the shortcomings of machine learning in general. And what they said is that graph networks are bigger than any one particular machine learning approach. It allows you to generalize about structure, things that individual neural nets just can't do. But as you get toward the end of this article, they're still wondering, where do we get the graphs that graph networks operate over? Well, of course, there are several of us in the graph industry space that have products and tools and all this sort of thing that think we can help with this problem. We think we can provide those graph data structures in order to run those algorithms and structures over. The issue with machine learning is that it eats a lot of data. So again, I mentioned earlier that machine learning takes iterations and it looks for improvements to make decisions. And so it uses past historical data, decisions that have already been made and what those outcomes were. Then it applies those to make new decisions and said, is this better than what I have before? Okay, keep iterating, keep iterating. So the problem is it needs a massive amount of data to iterate through in order to constantly improve and adjust to get closer to that end goal. So it takes a lot in order to help it learn how to process and handle that. So what we propose is that alongside your regular tabular data structures, so a lot of people have these grid types of formats that they feed into their machine learning models. What we're proposing is that you add on these connected structures, which is graphs, and you pick features from those and push those alongside the regular tabular structure into your machine learning model. And that will give you better and more accurate predictions than just the data you already have. So current data science models, of course, they don't handle these network structures, these connections and relationships very well at this point. So that's why you tack on that extra graph. Then you get that network structure component added in there. So a term we've kind of been using quite a bit is connection features, connected features. Basically, all those are features that are based on the connections inside the network. So it could be the number of relationships in or out of nodes. It could be the count of potential triangles in the network, or it could be neighbors in common, anything like that. You're basically condensing down the network structure to a few key features that you think are most important or most influential. Then you're going to extract those features, which is something that's already being done in regular machine learning models, where you basically condense your entities or your structure down into something that you think, you pull out those key kind of components of that structure and use that in order to run your predictions or your algorithms. So you're really taking the key bits of that data, the things that are most predictive or most influential, et cetera, and using just those pieces of that data. So then connected feature extraction just uses features that are coming from the graph and pushes that over into your machine learning models, just as you would regularly. So taking an example of this, again, we're going back to our Game of Thrones data set. This one's a lot of fun. So we have our data up here. You can see we have our traditional machine learning kind of tabular structure where we have names of characters, we have ages, we have the houses they're in, we have their genders, and we have whether they're alive or dead. So that's our yes-no flag there. Then we can run over our graph. We can run things like influence, so page rank. We can look at the number of relationships, and we look at the community that those individuals are in, and add those as additional columns onto our tabular structure. So now we know who has the highest page rank. We could look at the number of connections going in or out of the node, that's degree centrality, and then the community that that person belongs to. And you'll build out a model kind of like this. So you'll have various data sources all over the map. And you might push that over into Neo4j to kind of unify all that connected data, run algorithms, and engineer your features over that, and then push those features over into your machine learning model using a variety of tools. So one example we did for demos and kind of to test this out was a co-authorship graph. So we looked at academic writers who collaborated with one another and then tried to predict who they might collaborate with next, or who we could recommend they collaborate with next. So we were able to gather the data, public data set, and put that into Neo4j, kind of clean up that data and extract the features that we wanted to extract. How to do some kind of preparation for machine learning, so things like your train test split, your resampling, your upsampling, your downsampling, to kind of get the proportions of the data right, and then train those models using a variety of techniques, ensemble methods and such, and then evaluate those results. How did we do? We looked at the rock curve, which something characteristic, I can never remember that one, received something characteristic, and then the area under the curve, which is the AUC. And then we had a subject matter expert review. Is this good enough? Is this what we were looking for? And as you can see, the arrows here on the top, this is an iterative process. So you get to a certain point and you go, no, this doesn't look right. You back up and you kind of reanalyze or try some different algorithms and look at some various features. And then once you feel comfortable with that result over there on the right-hand side, then you're ready to actually push that down and productionize that. So just to take an example that we did, this is the co-authorship graph. This is just all of the authors that worked with one another, collaborated on papers together, and we put that into Neo4j as all the connections. And then we did a few different things with that. So we kind of layered some approaches. We have just the common authors model, which was this model you guys looked at back here. So that's just the straight generic Neo4j, just put the data in and look at the relationships. That's our common authors model. And then we have our graphy model, where we added on preferential attachment and total neighbors, which are link prediction algorithms. So that kind of became a new model, an improved model. Then we added some triangle counts, so min-max triangles and the clustering coefficient. We calculated those algorithms and kind of created this new type of model, this added layer. And then finally, we tacked on a few more community detection algorithms with label propagation and Louvain modularity to kind of run some clustering analysis over the group, and that added our fourth and final layer. So we used all of these different features to train the models and kind of do a compare, what were the best, what were the worst, how did that stack up. And this was the rock curve and AUC that we got out of it. So you can see that just our random average distribution is that 0.5 going straight up into the right. And it's a little bit hard to see maybe, but just our common authors model, so just dumping the data into Neo4j and looking at the relationships, we were able to get a 0.85 AUC with that green line. The next model that we did, we added those, that one was the DRAT. Preferential attachment total neighbors, that's it, the graphy model. So that's the red line then going up and over. So now we've got our 0.95 AUC. And then finally our triangles, which is 0.98 in the blue. And the last one being our community model, which is the pink line at 0.99 area under the curve, which is quite a good result. And you can see here we ran some analysis for accuracy, recall, and precision over these models. And our first model, our precision was actually really good. So it was almost 97%, but our accuracy and our recall was, it was all right. But then by the time we got to the end, so we stacked on all these models, and so we had up to now model 4 with all of these extra network models, our network features, and now we have almost 100%. Area under our accuracy, recall, and precision. So that improved our results drastically, actually, even just going from a basic connected network structure inside Neo4j to finally adding all of these layered features that are based on the connection and the network, and adding those into our scores. So with this, graph data science grants us higher accuracy using things like connected feature engineering to pipe that into our machine learning models. Now we're going to kind of take it even further. So I want to show you guys just a few examples, live examples of some of the main use cases that this stuff is being used for and how users and customers are doing this stuff. And then we're going to start looking ahead. So what's kind of on the cusp? What are people experimenting with, and what's to come, and what Neo4j is looking at doing in the future? So first of all, there are plenty of applications where this stuff is being used right now. So it's being used in financial crimes to fight fraud rings and fraudulent transactions in banking and investments and money, looking for money laundering. We can do drug discovery, so looking at, we have this certain drug that's being used to combat this specific disease. Can we use that drug that's already on the market, already been FDA approved? Can we use that to fight other diseases, things that might be similar or connected somehow? Recommendations, so I understand what a person has bought in the past, but can I recommend products and services to them that maybe their friends like, or maybe because of the industry they work in, or the things they might like to do on the side? Can I recommend better and more relevant products to them and services? Customer segmentation, so understanding which areas and which targets your customers fall into and being able to target that audience better for advertising your products or services, better to help better satisfy them. Cybersecurity, so looking at how you can build up your network, what things might be vulnerable, and how you can improve that. Churn prediction, looking at can I predict when a person will churn from my company, and when they do churn, what will they take with them? What are all the side impacts of that? So if you have a parent that leaves your services, it's very, very likely that children or grandchildren or aunts and uncles, anybody they happen to be tied to, that might also impact their decision, and they could also churn. So not only are you predicting when they might churn and what are the kind of triggers and factors that might get them to churn, but what will they take with them when they go? Predictive maintenance, understanding when something needs fixed and trying to fix it before it gets to that point, before it breaks and causes problems. And then finally, where a lot of this all started to begin with is search and master data management. So how can I get better results for things users are looking for? How can I give them more valuable information? So this is kind of the stair-step trend that we're seeing right now, with our lower line here being enterprise delivery. So you'll start kind of in that lower left, and you'll kind of move to the right as you start understanding and getting better acquainted with how this stuff works and how to utilize it to your best advantage. And then, of course, as you move up on the vertical axis there, you're getting more and more complex and deeper into this stuff. So we're going to start with the lowest and easiest, which is query-based knowledge graphs. There have been a lot of these out for several years. This stuff is tried and true by now. You have a ton of vendors using knowledge graphs in order to tackle just kind of some search and valuable information types of problems. The one we really like to talk about, and one that I absolutely enjoy sharing, is from NASA. I'm a long-term astronomy fan. So back in 2012, NASA was getting ready to handle the Orion project. And they knew they had built a similar capsule back when they were doing the Apollo project, but they couldn't find the valuable information that they needed from their lessons learned. So they had all of these documents with all of these lessons in them, and they couldn't find the information in order to look at the specific parts and the capsule that they built back on the Apollo project to apply then the goods and the bads of that project to this new one. And so they ended up testing out Neo4j, I think somewhere around 2012, 2015, putting all of their lessons learned into Neo4j, and basically creating this knowledge graph where users would get in and search for a certain term, and it would come back with relevant results. So before, they were having to look through these millions of documents. Remember that NASA is over 50 years old, so it's accumulated over 50 years of data and lessons learned. So trying to sift through those millions of documents for valid search terms was just a nightmare. So doing this in Neo4j really helped them out. Of course, it was kind of a quick and easy win for them. It saved over 2 years of work and $1 million of taxpayer funds. You shouldn't necessarily be looking for these massive, easy, quick wins. You may not always get those phenomenal results from your projects, but what you should be looking for is delivering valuable and better and faster, more efficient results for the data you're looking for. So next we're moving on up. We're going to go to query-based feature engineering, which is quite a bit of work that Neo4j has been doing the last few years. However, it still does require a subject matter expert to know something about the data that you're dealing with. So you need to know what section of the graph is important, what types of things am I looking for in this particular type of data set. And so it really requires someone who's familiar with that domain in order to pick out and point to the areas you need to focus on. One good example of this is Hetionet, which you can find at het.io. They're actually using Neo4j, and you can actually write queries and stuff in our Neo4j browser, and it's available on the web. But this is over 50 years of biomedical data, and they're using this data that's published and public to predict new uses for drugs, using the graph topology to look at features and predicting new links for that. So you can see our data model here is just genes, looking at different compounds and diseases and the anatomy and side effects, et cetera, and trying to find new links between certain genes and diseases, as is in this case, in order to see if you can use drugs to fight those new things. So again, this requires a subject matter expert. You need somebody who understands biomedical data, who knows kind of what they're looking for in order to make these links. So in this example here, we're looking at the gene IRF1, and we're trying to see if there's a link that we can find between that and the disease multiple sclerosis. So you can see that there's no direct relationship between the two, but knowing what all is associated around it and how it's all connected, can you predict there being a link between these two? So you can run calculations looking at the different pathways to get between the gene and the disease itself. And this is using a weighted path in order to run the calculation there. Oh, nope, that went on. Okay, that was it. So looking at and scoring what is the most probable way that we can get from this gene to this disease. What's the most probably likely scenario and connection for these two. So next, looking at graph algorithm feature engineering. This is where we've been focusing quite a bit of our time in the last probably year or so. Graph algorithms, remember, are somewhat unsupervised. That means you don't need that subject matter expert to tell you what piece of the graph or how to understand the data that you're dealing with. You just kind of want to know what you're looking for from the data, whether you're looking for a path or influence, et cetera, and then you let the graph algorithm tell you what's important in that data set. So which nodes are influential, which clusters you might want to look at in more detail, et cetera. So this doesn't require that subject matter expert intervention. As we kind of talked about, these are kind of the areas of algorithms that Neo4j has dealt with. You'll see that there's a sixth one kind of added down here in the right-hand corner. We are starting to work on graph embeddings and providing some algorithms for that. However, these are by no means production ready. They're still kind of prototypes. But we are starting to work kind of in this space, and I'll talk a little bit more about what these are. But it's basically learned representations of the connectivity and topology. So using graph feature engineering in a live use case is very common in financial data, financial fraud. So there are a lot of banks using this already using various tools and vendors and such. But graph-based features improve a lot of accuracy. These are some of the 4 that are being used right now to combat some of this stuff. So connected components looks at disjointed sections of your graph. So if you have a graph that's very interconnected, as a lot of users are, but all of a sudden you see this cluster that's kind of off by itself and not connected to much, that's might be a good indication that that's kind of a fraud ring. That's kind of segmented, that's unusual behavior. PageRank, looking at influence and transaction volumes. If you have a ton of transactions moving through a single user or a couple of different accounts, that might be suspicious and something that's abnormal. Louvain, looking at communities that frequently interact. So if you know you have a fraudulent user and they really interact quite a bit with a couple other users, that might be a fraud ring then. Those might be connected. And then Jacquard similarity basically looks at the transactions and how similar the transactions and patterns and properties of 2 accounts are, and say, are these accounts, maybe one's a copy account or a fraudulent account, or maybe they're both fraudulent accounts because they're both doing something that's abnormal. So just in case you think that Neo4j is new and great in this space, it's not necessarily so. There's over 48,000 patents using graph algorithms in order to combat financial fraud over the last 10 years. So this is kind of the list of some of the algorithms that are being used in that space. So we are by no means the first or the newest in this, but people have definitely been working on this stuff and applying this to try to catch bank fraud a lot easier. I did probably mention that we have a lot of algorithms in our library. This is kind of the list as it is right now, but really it's just about, remember network science is very, very broad. There's a ton of algorithms and research in that space, and we just start adding technical implementations for the network science algorithms that people want or need in their type of industry or in their use case. So this list will continue to grow as we come across examples and use cases where people need something else or we don't offer the algorithm that they need, etc. Okay, hopefully you guys are still awake because we're about to dive in just a tiny bit deeper into graph embeddings. This stuff can get a little bit mind-boggling, but my goal here is to kind of explain these in very real applicable examples where even if you don't remember the very specific mathematical definition, the functionality and the logic make sense. So I'm not overly mathematical and I still really love this stuff. So looking at graph embeddings, embeddings transform graphs into a feature vector or a set of vectors that look at topology, connectivity, or attributes of nodes and edges in the graph. Okay, let's kind of rewind and back up. Basically what it's doing is it's taking a graph and condensing it into a vector or set of vectors, which is just kind of like a float or array of floats that basically a machine can read and say, this is the structure, this is the calculation of this network in a single vector or set of vectors. So it's condensing and flattening all that very complex information down into a single machine readable byte that it can handle. So there's a couple of different embeddings. You can do vertex or node embeddings, which look at the connectivity of nodes, individual entities. Path embeddings look at traversals and pathways across the graph and condense those down into a vector or set of vectors. And then finally, graph embeddings, which encode an entire graph into a vector in order for a machine to say how similar are these two graphs to one another because it can compare those vectors. So a good example of this is the deep walk approach. That's the image down here. So looking at a random walk, which all a random walk is starting from a point in the graph and just randomly traversing through the network. So it's often, I think, called the drunkard's walk, where it just literally just goes around and hits different endpoints in no certain order. It could go back on itself and revisit places it's already been, et cetera. And so it's just looking at various paths through the network. So you come out with several random walks, you'll end up with this list of pathways that you can possibly get through your network. You'll train a skipgram model on that, which basically just means that you're going to look for the most predictive paths. So what are the ones that come up the most often? What are maybe the most central hubs that it seems to hit quite a bit, et cetera. You'll find the most predictive ones and then condense those down into an embedding, which it will read later. So if you're familiar with word2vec, this is actually how word2vec works. So you could, for example, look at books, and you want to find the similarity of books. But you don't really want to read every book on the market in order to determine this book is similar to that one and that one and that one, and here's why. So you can actually do something like this, an embedding, in order to handle this. So it takes a graph, and does some random walks through the books and the categories and the authors and the words in that book, maybe. And then it would kind of create all those different pathways through. It would train that skipgram model, so what's most predictive? If the word the appears in books, that's probably not all that predictive. It's going to appear in a lot of stuff. That's not going to tell you much. So it looks for the things that are most influential, the things that are kind of unusual, maybe. For instance, if you like 16th century poetry, that's probably a better indicator that you're more similar with another person who likes 16th century poetry than if you like Game of Thrones, because there's a ton of people that like that. So that's not very predictive or really a key component of that similarity. That doesn't mean that I'm extremely similar to somebody else who likes Game of Thrones, because there's a ton of people that do, that are not very similar to me. So 16th century poetry, more unusual, kind of rare thing, that's probably a better indicator of how similar those are. And then finally, you'll calculate those more predictive models, more predictive paths down into that embedding. This is actually being used at eBay right now. I believe this is the name of the article if you want to read more information about it. But if you have a user, Alice, that likes a particular song, which is Shape of You, that's by Ed Sheeran. And so it goes against the knowledge graph that's kind of here in the center, and it calculates all the possible paths. What are the possible recommendations that a user might like some other song? How can we recommend songs that she might like better or alongside this one? So it'll traverse all these paths through the network and basically come up with this kind of grouping and listing of paths. So we have all of these paths. We're going to find the ones that are most predictive. So maybe in the same genre, that might not necessarily be as predictive as liking the same artist, several songs from the same artist. Or she might like a particular style of singing that maybe is more predictive for certain artists than others, etc. So it'll find all of these pathways through the network, and then it'll calculate that which are the most predictive, and then come out with an embedding. I can recommend this song because it's most similar to the pathways that you've liked previously. Okay, one last one. So we're adding yet another layer. We're going on to graph neural networks, which is basically deep learning looks to train multi-layer neural networks using gradient descent. A lot of very complex words there, but basically what it's doing is it's taking a graph, an entire network structure. It's doing kind of some computations and some processes and steps and possibly some changes and things in the middle, and then coming out the other side with a graph output. So so it basically just takes a graph input, a network structure input, does some computations and some things in between, and then gives you a graph back. So one thing, actually, if we take our smoker or our voter example, so for instance, you're going to start with an edge update. So let's say they become friends with a new person who happens to be a smoker. Okay, you've got a new relationship there to this person with someone who's a smoker or voter, et cetera. And then, okay, so because of this new relationship, do we need to change the property of this node? Is this person now a smoker? Okay, are they not? You can update the property. And then you look at the overall graph. Do I have now more than 50% of users in my graph that are voters or smokers, or do I not? Did that change the overall structure of my graph at all by making that small relationship change that may have impacted my node, that may have impacted my overall graph? So there are very few use cases of this just yet. This is very on the cusp experimental, but one good one is chemistry. And I think this example makes a whole lot of sense. And again, I'm not a huge chemist or really into those details. But if you take two reactants and reagents, what will the products be? So predicting, we know we have this history of when two chemicals or atoms react. We know we get this other process, and these things happen in the middle. So based on those two things, can you predict what's going to happen when two new chemicals or atoms get together and what the process there entails? So not only what will the product be, but how does it actually, what steps does it take in order to get to that final product? So we get our, you can see that these chemicals are kind of graphs. So you have a graph over here with one reactant, two reactant, a reagent. So that's graph A. Then something's going to happen, some steps and processes are going to happen to that, and you're going to get a whole new graph out the other side. It's going to be completely different. And then you can mark what the steps it took, what were the steps it took in order to get that final product. So looking at the process of this, we have our two reactants here. It's going to remove this Li atom here on the end. It's going to bond and remove that. Then it's going to say, do we have a stable structure yet or not? Do we have a stable chemical or atom just yet? No, we don't. Okay, let's keep going. What process do we need to do next? It's going to add a bond here in the middle. Okay, am I stable yet? No, keep going. And then it's going to remove, notice we have two bonds between this oxygen and carbon atom. It's going to remove one of those, and all of a sudden now we have a stable graph, totally different graph out the other side of that. And now we can understand not only what it produced out the other side, but how it got there. So this kind of reduces and eliminates kind of that typical black box of AI where you don't understand why it's giving you that output. You don't understand what your model or what your algorithm is telling you. With this, you understand exactly how it's getting to that point and what steps it took to get there. So graph data science in this area gives you better trust and applicability because now you know what steps it took and how it actually got to that particular point at the end. So that's graph native learning. So now we've covered this entire process. Hopefully you guys have all stayed with me for the most part. But starting out, just be aware that you don't necessarily jump in at the end. Those things may look really cool and really powerful, but it's probably better to build from the ground up. Start from something that's pretty simple to implement, might take a subject matter expert to kind of help you along, and then move on to the next step when you feel like you have a good grasp and good results coming out of that. So just some resources to leave you with. If you're a developer or data science, you can actually test this stuff out. We have online instances in our sandbox that you can run graph algorithms and some of the other things on over some data sets that we just feed out of the box, or you can pump in your own. We have some online training, one for algorithms, applied graph algorithms, as well as one for data science. They're free online trainings that you can kind of walk through self-paced to get an idea of how Neo4j goes about these problems. Our community site, you can ask questions or hear about what users are actually doing in this field. And then we do have a free ebook out on our website still for graph algorithms. Talks about all of the algorithms and areas as well as machine learning there at the end. And if you just want to find out what are some of the use cases and areas that this is being used and applied to, check out our use cases section for artificial intelligence and analytics, as well as knowledge graphs. Again, knowledge graphs are pretty substantial and reliable now in the industry, so that's a good place to start. And then if you're curious about what products we offer in the space, you can go out to our graph machine learning algorithm section of the website and kind of look at that. So with that, again, please feel free to reach out to me, Twitter, email, LinkedIn, however you're most comfortable for continued discussions and questions. And thank you so much for bearing with me for this hour. And I hope you enjoyed Box Days BIF, and I hope to see you next year.